So I wanted to talk to you about embedded software. You probably don't know the term of embedded software, but you're going to be surprised how much you know about embedded software. There's all types of software. There's application software. You probably all use Microsoft Office. You probably all see the Avatar movies. There's lots of software in those nowadays. The Android phone, lots of software in those. Cars, you're going to be surprised to hear how much software is running cars nowadays. And the gaming. But today, I wanted to talk about embedded software. And it used to be called firmware. It's really the code that you're putting down onto the processor in a handheld unit, the unit that has like a keypad or communication, sometimes video. It's mostly microprocessors that are running without a GUI interface. So let's think for just a minute, how many microprocessors are in your house, right? So there's, in the average household, there's 50, considering your TV, your dishwasher, your washing machine, some of the toys, right? All of them are running in your house, and half of them are running in the car in your parents' garage, just for you to know. Down here are the places in your car that run code, like the airbag system or the alarm system. And so a premium class automobile probably contains close to 100 million lines of software. And that software executes on 70 to 100 microprocessor-based electronic units. And that's a premium car, of course, but that's a quote from Manfred Breuer. And then, just to give you an idea, the avionics for some of the planes, for the F-22 Raptor, has 1.7 million lines of code. So it's kind of a surprise, isn't it? Now here's the big one. 0% of the world's microprocessors are used in computers. Yep. Every PC, Macintosh, engineering, workstation, Cray supercomputer, and all the other general purpose computers put together account for less than 1% of all the microprocessors sold in the world today. If you round off the fractions, embedded systems consume 100% of the worldwide production of microprocessors. Is that a surprise? It was to me. So the thing about innovation in software and development is that software and hardware development relative to computers is full of paradigm shifts. So I wanted to give you an example of a couple and then leave you thinking about what's next. So technology evolves like this, right? There's the S curve there at the bottom. Technology is evolved, then you build on it, and you learn from it, and then all of a sudden it sort of diminishes its returns, right? And it's time for the next evolution in technology. So let's talk about some of the evolutions in computer technology, right? So there's this Moore's law. And it's an observation that Gordon Moore, the co-founder of Intel, back in 1965 made, that the transistors inside a microprocessor will double every 2 years. It's called a law. It's an observation proven by, the data for since then. It's very interesting. So why are transistors important for you, for memory, for the software? Well, among many things, it's the addresses of your code. Right, so I just said that there's 100 million lines of code in your cars. There's 1.7 million lines of code in avionics. Now, of course, none of those go in any one processor. But I want to talk to you about the address bus. Okay? So, for example, say you were addressing houses and you were only allowed to use one digit to address the houses. How many houses could you address? One digit. 9. My daughter said 9, but in software and hardware, you're allowed to use address 0, so it is 10. Okay? Only 10, if you can only use one digit. So, but if you could use 2 digits, it's 100 houses that you could address, right? And in each of those addresses in a processor is an instruction, right? All those codes that you write take up addresses, and so the increasing size of a chip makes it so that you can have more code, right? So So one of the big paradigm shifts over the time is the size of processors, right? So in 1970, we started with a 256-bit RAM, and then grew to 16-bit processors, 32-bit processors. If you buy a computer today, it's a 64-bit processor. That means there are 64 address lines, right? So how many addresses does that mean you can do? Well, look at that. It's 16,000 terabytes, right? Or 16 exabytes. That's how many addresses. Well, that doesn't seem like, it's hard to grasp that. So we're trying to figure out how to think about it. So we were thinking, okay, so how much money would you have to spend every day of every year for 80 years in order to spend 16 exadollars? Right? That's how many zeros that is, by the way. So $32 trillion every day for a year, for 80 years. Okay, so that's how much address space there is in software now. Okay, so clock speeds, another thing that changed over time. Right, we stopped very small, started 2.5 megahertz back in 1976. We were up to 2.6 gigahertz in the Pentium 4s. So here's kind of the graph of the clock change over time. Now, in just a minute, I'll explain to you why we sort of hit a wall, but it's sort of an electronics, it's sort of a hardware wall, right? The physics of electronics makes it so you can't have clock speeds going above a certain speed, okay? So we had to innovate a new paradigm change, and come up with how to increase your functionality, increase your speed of execution with the same processor, right, over time. So let me tell you a little bit about product development components, right? There's the hardware, and that's the hardware platform that you're on, right? We call that the board support package, because quite often you have a big chunk of software that you're wanting to put on different platforms, right? In our business, we have lots of communication networks, so we have Ethernet and ControlNet and DeviceNet, right? And those are all of our networks that we want to put our platform on, so all that code has to be platform independent. And then our development tools, right? And I'll show you a picture of my development environment I just copied. So the embedded software industry, we started with assemblers. So for example, in the late 1980s, I worked at Tandy, and I was a software developer on the universal remote controls. It was an 8-bit processor, very small memory size, and we had to hold all the code for all the different types of IR that we were going to send out to all the different types of TVs and VCRs in that space, and I was using assembly code. Okay? But then all of a sudden we got more memory, right? And so we could use larger compilers, or we could use more complex code like the C instead of assembly. So the larger systems, we could add operating systems. So an operating system on your computer makes it so that you can run Windows and Solitaire at the same time. And in the little microprocessor and the microcontroller business, right, well, there's several things that we need to be doing at the same time. We need to be listening to a keypad. We need to be outputting to the display, right? So there's lots of things that it needs to be. So we need this operating system. It's not as heavy as the operating system in your computer, but the larger memory sizes and the controllers made it so that we could put operating systems in embedded software and support, of course, additional functionality. That's what we always need to do. Faster, and more functionality. So all of a sudden we were given the gift of memory space, and we invented all this code, and now we have a complexity problem, right? And complexity problem makes it hard to sustain the code so that one person after another can keep the code, change the code, update the code, right? So when it's complex, it's harder. And so we solved the problem with abstraction, with the C++ code, right? So we could use the C++ code and use objects, or so if you want to break a big project down into smaller pieces, make smaller pieces, we call those objects, and we abstract the data away. It makes it easier for us to use the same code for again, like I was saying, the different platforms. But again, the complexity was a problem. And the abstraction was to the rescue, dividing and conquer the products, or the code into. So software solved the complexity problem, or began to solve the complexity problem. And we could use templates now, and we could use design patterns. And these are just templates of code that are accepted among everybody. That's the best way to do some chunk of functionality. And then, of course, the threads, like I was saying. But that brings us up to date. So you kind of understand that we've changed the hardware a whole bunch. We have all this code space. We've changed the clock speeds, so we now have fast execution times. And we've changed, of course, I didn't mention the architectures of the computers changed, pipelining and caching. So there's a whole lot of other functionalities that makes it so that we all of a sudden have this huge resource to produce code, quick, fast code functionality. And we've had to add security now on the codes too. But like I said, remember the clock speeds, and up here where it has the point. And we hit kind of a clock speed wall, and we decided we weren't going to be able to just keep increasing the clock speeds. So what we did was we changed the number of microprocessor cores inside a processor, right? So before we had one ALU unit, and now we have several different cores inside our processor, and that means that we can, instead of having one core running a couple different threads, we can have 4 cores or cores, so, or more than that. But at Rockwell, we're creating our own ASICs now with 4 cores. And when the cores went up, the clock speeds could drop, right? But you see that it kind of came back to our max. But so the multiple cores is our next tier of problems, right? So now we have the multiple cores, and there's problems with that, right? So now we have 2 different computers inside one processor accessing the same memory space, because you're going to want to share memory, right? You're going to want to load share, right? So it's easy to have one core on this one run the communications unit, and one core on this run the video display. So it's easy to load share like that. But then what happens if all of a sudden the video component has too much? There's no way to offload it, right? So now we're having operating systems of operating systems. We're currently using the hypervisor at Rockwell, but you know, it's a very complex problem that we're just starting to see, right? So it's like that big iceberg underneath the water. We're starting to see the complexity of the problem, and so we're going to need to make a paradigm shift. So here's the problems. Concurrency, accessing the same software or the same memory. Non-determinism. So here we have two cores, right, running different things, right? It's got its own tasks that it's running, and this one has its tasks that it's running. And they're totally independent of each other, but oops, this task on this core and this task on this core has to happen before this task on that core. Well, how do you do that? Right, that's called determinism, and that's a real problem in our multi-core world that we're trying to solve it in hardware. But this is where we've kind of come up against, so our current technology has kind of come up against the wall of the new innovations, right? So this is where you guys come in, right? So, oh, and one more, the development products. So when it comes to the code that I write, and I have a development environment, I call it the integrated development environment. It's very easy to plug into one core, right, and debug that one and what it's doing. But it's hard to debug 2 cores at the same time, because it's hard to stop them at the same time. You know how fast processors go, you send them a stop, they could be stopping in, you know, millions of nanoseconds apart in code, right? So the development tools have to improve. So all these problems that I was talking about, the concurrency, the determinism, has to be multiplied by the number of processors that are going in cores. And they're even saying that C++ is not going to be able to solve the complexity problems currently. They're saying that threading is not going to be able to handle the multiple processes that would go, right? So if you go into any of the magazines that they're reading nowadays in embedded software, they're saying it's time for a paradigm change. So time for a bunch of folks that have good new innovations to come in and see what's next. I wanted to show you what the picture of my development environment is at work. I work on Right now, I'm debugging an ASIC that they're making with 4 cores for our new faster backplane that we're making. And so this is my software development. So you can see I have my software in the middle, all the functions in this current file right there. So just wanted to give you a glimpse of what it looked like. And this is my integrated development environment. So this is when I'm actually plugged into the processor on the board, and I'm executing these instructions one at a time. So here's all the list of the code, right? Here's the code I'm actually running. This is the memory. I'm looking at the memory on the microprocessor. So when I think that this bit should be set, or this value should be some number, I can look at it. So here's my registers, if you're very familiar at all with processors. Here's the registers, right? The PC, the program counter, the address that I'm actually at. Stack pointer, right? The disassembly, so this is my code in C. This is the disassembly, right? So that's my development environment. That's what, if you're working on software, like I am, and you're developing a product in embedded software, this is kind of the tools that you'd use. So the future of hardware and software development is more reconfigurable software, okay? Self-optimizing software. Other than the problems that I've talked about, these are some other things we need to think about. Security enabled, right? I mean, everybody has downloadable firmware somewhere in some item. Well, not everything's protected from somebody downloading something that's not good, and that's starting to happen. So we're having a lot of security discussions at Rockwell. Actually, that started a little while ago. And real-time configurable hardware. So these are the tools. I've told you the problems. So that's just what's coming up next. And it's a very exciting time in software development, if you can believe that, but it is. Okay, so that's my presentation.